So, how do we solve indicial equations using these logarithms? Well, first question to ask ourselves is, what is an indicial equation? And here is an example of an indicial equation. 10 to the power x equals 36. We've got to find x. And if you just pause for a minute and think about it, that's not a straightforward thing. You've got a calculator, you could try putting in different numbers for x and then see until you home in on 36. That's a bit of an unsatisfactory way to do it, but in fact in some really awkward equations that's actually what you end up doing, trial and error methods. There are certain things that you will learn later on in your maths if you carry on the course that do that sort of thing, trial and error. But we want a more elegant way of solving this, and luckily there is. This is an indicial equation because it involves the power, either the unknown, the thing that we're after, or the base is the unknown. And so we've got to find out what that is. And we use logarithms to do it. We solve them using logarithms, normally to the base 10. So logarithms then, we use these logarithms, as I said, to try and solve these indicial equations. Once we get used to what they are and using them, they're actually quite straightforward, and the calculator really helps us a lot. But to define a logarithm is not always an easy thing to get your head around the first time you see it. A logarithm to the base 10, for example, is the power to which I have to raise 10 to get that number. The logarithm of a number is the power to which I have to raise that number, in this case 10, to get the number. And so the easiest way is to look at an example. If we so we can think of the logarithm almost like an inverse function, to undo to the power something. Look at this example. For example, the one we looked at already, 10 to the x equals 36. What do? We find what's called the logarithm of 36, and your calculator has a logarithm button on it. So if I hit logarithm of 36, it will tell me what x is. Because logarithm is usually to the base 10 or often to the base 10 on the calculator, and when we write it down, you often don't bother to write the 10. So log on its own means to the base 10. So if you type into your calculator log of 36, what do you get? Because this x that we've just found, this logarithm rather, is a power of 10, then a small change in the power can mean a big change to the number. So we generally quote it to a reasonable number of significant figures. Okay? And what that's saying now is that 10 to the power, so therefore, according to what we've just been doing, 10 to the power 1.556 should equal 36. So if you put that into your calculator, 10 to the power 1.556, and it's no coincidence that 10 to the power is above the log button, what do you get? You see we get 35.97 to 4 significant figures, so close to 36. And the more significant figures we add, the closer we will get to our answer. So there is a rounding issue associated with this. Generally, when you use logarithms, you have to round the numbers, and 4 significant figures is not an unreasonable number. Okay? So that's what the logarithms do. The logarithms allow us to find the number when we've got x being in the power in this case. Okay? But to solve more difficult indicial equations, we need to know these laws of logarithms. So let me just show you what these laws of logarithms are. Remember, the logarithm is a power, usually of 10. So the laws of indices apply, but they're written as the laws of logarithms. So we have these laws of logarithms, but they really are just the laws of indices if you look at them. if I've got two numbers multiplied together, remember these are powers. When you multiply, you add the powers. So we add the logarithms, which are the powers. When you divide numbers, you subtract the logarithms. And when I've got one power, which is a logarithm is a power, so this is the key one, which is why it's asterisk. If I've got one power raised to another power, I actually just multiply the powers, if you remember back to the laws of indices. So the power comes down and goes in front and becomes a multiply. And as we'll see in a second, that's the key one, which is why it's asterisk. I've added one other. Remember, anything to the power 0 is 1, so the logarithm of 0 is 1. Worth just jotting that down. So there are the laws of logarithms. So let's look at this again. This 10 to the x equals 36 that we thought of it. We think of it as an equation in the sense that whatever we do to one side, we must do to the other side. So we actually effectively took the logarithm of both sides, which meant that the log of x turned out to be, turned out to be the log of 36. Let's look at another example here. 2 to the x equals 12. X is in the base, is in the power, so it's an indicial equation. So what we do is use logarithms. And earlier we were talking about adding something to both sides, multiplying, dividing, and so on. As long as we do it to both sides, we're okay. It's the same in this case. What I do is I take the logarithm of both sides. The logarithm of 2 to the x equals the logarithm of 12. So try to show it with the colour. We've just taken the logarithm of both sides. Now, if you remember the laws of logarithms that I've just written down, or you've just written down, that third one, which is the key one, tells me that a power comes down and becomes a multiply. So that x can now come down and go in front and become a multiply. So therefore, x times the logarithm of 2 equals the logarithm of 12. And we can, in practice, when we've done a few of these, go straight from that line to that line. We take log of both sides, which means that the power comes down and becomes a multiply in front, like that. Okay? And that is the step that you will use all the time when you're solving indicial equations. First thing, take log of both sides. Second thing, bring the power down and put it in front and turn it into a multiply, because that's what logarithms allow you to do. And now, remember, logarithm of 2, you just looked up the logarithm of 36. Logarithms are just numbers, that's all they are. Quite long numbers, you have to round them generally, but they are just numbers. So if I want to get x on its own, all I do is divide both sides by that number, log 2. So x becomes log of 12 divided by log of 2. And now I reach for the calculator and work out what that is. So x 3.585 to 4 significant figures. If you are using, and these are not uncommon in indicial equations in engineering scenarios, as you'll discover, how would you check that this was right? Go back to the original equation and put that x in. So let's see if 2 to the 3.585 is 12. Check. 2 to the 3.585. It's unlikely to be exactly 12 because of rounding, but hopefully it will be reasonably close. Pretty close. Okay? Because we held the accuracy, we get a reasonably good answer. So it's a good idea to hang on to this accuracy. Okay? Little exercise, solve this. Just pause the video, you have a go at it, and then we'll look at the answer together. So, I'll take log of both sides. Because I've taken the logarithm of both sides, that x can come down and become a multiply. So x log 5 equals log 36.8. So I've done two steps in one there. And then divide both sides by log 5. So log 36.8 divided by log 5 equals, sorry, 2.2402, so okay. And then we can check by putting that back into the original equation and see if 5 to the 2.2402 gives us back our 36.8. So how about this one? We'll look at this together, but see if you can suss it. What difference is it going to make that in fact it's not an x, but it's an x plus 2 at the top? Follow the steps, see what you get. See if you can get the answer. You'll know you're right because you put that x back in here, and 4 to what that power will give you 13.8 if you're correct. So I'll just pause this, have a go, and then we'll look at it together. Okay, so, right, first step, take log of both sides, which means that the x plus 2, still in a bracket, can come down and multiply. So that's the first step. It doesn't matter what the power is, it just comes down and becomes a multiply. In this case, the power is an expression, x plus 4. So, next step, divide both sides by log 4, that number, get rid of it. So x plus 2 equals log of 13.8 over log of 4. X has got 2 added, so subtract 2 from both sides. X turns out to be log 13.8 over log 4 minus 2. So now I can do that in one hit on the calculator using the fraction button, and I get x to an appropriate number of significant figures. So x turns out to be negative this time, negative 0.1067. So to check, 4 to the power minus 0.1067 plus 2 turns out to be pretty well exactly 13.8. Okay, so we check. When you come to do the assignment, check. You'll know you've got it right before you hand it in. Last one to look at today. What happens if the unknown is the base? So have a look at that. Write that down. Same start point with something like this. Just because the unknown's in the base doesn't matter. The first step is still the same. But this time we're going to end up with bringing the power down. That's 3.6 times the logarithm of x equals 120. So x is inside the logarithm now. Divide both sides by 3.6. The logarithm of x equals 120 divided by 3.6. Work out what that is. The logarithm of x equals, now we have to remember what the logarithm is, okay? Remember the logarithm of a number is the power to which we raise 10, in this case, base 10, to get that number. So in other words, x equals 10 to the power 33.33. Yeah, that was going to come out to a massive number. The error that I made, spotted by, to give it Teddy his due on the video. At this point, I forgot to log both sides. Okay, so in fact that should be the log of 120, which means that's a log of 120 over 3.6. That's more like it. Which means the log of x is, so what is the log of 120? Okay, so log of x is 0.5775. That's a bit more sensible. So x equals 10 to the power 0.5775, which is so we have x equals 3.780 to four significant figures, so 3.78 to the power 3.6 should be round about 120. Near enough, okay?